Good morning everybody, I'm Mario Spirito and I'm presenting the work in Outer Decomposition for strictly proper linear time invariant systems and no minimum phase performance limitations accepted to CDC 2022. So during this presentation we talk about the stabilization of minimum phase systems. In particular, I will give a problem formulation, let's say to introduce the problem we want to solve, give an introduction to what is the inner-outer decomposition for a simple example of transfer function. I will then present the extended inner-outer decomposition for multi-input, multi-output systems that are strictly proper. We then present a realization of such inner-outer decomposition and talk about its input-output equivalence with the original system realization. We then give an application of such inner-outer decomposition to the stabilization on minimum phase systems and show an example of an inverted pendulum on a cart before giving the conclusions. So, about the stabilization on minimum phase systems, the problem we want to solve is about achieving robust stabilization on minimum phase systems via dynamic output feedback by reducing some performance loss. In particular, we consider a minimum phase linear system whose transfer function is given here with unstable 0, Z1, and let's say two stable poles, P1 and P2. We can always extend such transfer function by adding a stable pole 0 cancellation, thus introducing the two new dynamics. In particular, we consider this stable 0 pole cancellation. We thus have obtained a minimum phase system in cascade with a non-minimum phase system which is stable. We indeed actually found the outer and inner terms of the original plant. So in particular, if we look at the step responses of the good twin obtained by this decomposition, here shown in blue, we actually see that there is no undershoot, while the real output, which is also the output of the cascade between the outer and the inner system, has the undershoot as an undershoot characteristic in the step response. The performance losses we want to deal with we dealt with in this work are about the gap between these two step responses. And yes, in order to deal with this, we introduce the concept of inner-outer decomposition, where the inner factor is a non-minimum phase system but stable, whose self-adjoint operator is the identity map for all frequency in the complex plane, and its zeros are all in the right half plane. While the outer factor is minimum phase, has the same pose of the initial plant, and its self-adjoint is equal to the original plant self-adjoint. Mainly in literature we have only results for MIMO systems for purely proper systems and in a frequency domain. In order to deal with the inner-outer decomposition for strictly proper systems, we consider its state space representation in normal form, where we assume there is no zero dynamics, no zeros on the imaginary axis. In order to compute the inner-outer decomposition, all we have to do is just solving an algebraic Riccati equation, looking for the stabilizing solution x, such that the spectrum of f minus gg transpose x is in the left of plane. And this will give us the inner-outer state space representation, here reported in equation 2, where the system on the right is the inner system and the remaining part of the dynamics is the outer system. The equivalent cascade representation is reported here on the right side. So the steps to obtain the inner-outer decomposition realization starts with taking the zero dynamics of the system self-adjoint, but in the state space realization, which is an Hamiltonian system to which we can associate the algebraic Riccati equation shown before. When we find its stabilizing solution such that the spectrum of f minus g transpose x is in the left of plane, we can thus define the stabilizing trajectory y star, which is equal to minus g transpose x z. Then, applying a backstepping technique to the real output of the plan, we can define the outer output yo, which is equal to y minus this stabilizing trajectory y star. And thus, we take as outer states xio, obtained from the definition of the outer output, and stacking it with the z state of the original plant. And then the inner system is just a copy of the zero dynamics, and the output of such dynamics becomes the real system output. Thus, by the definition of the outer coordinates xo and z, we can define a map between from the initial plant state to the inner-outer decomposition. So we can actually see that the outer dynamics is by definition of the stabilizing trajectory. The outer dynamics is minimum phase, and the inner dynamics is stable, but its zeros are the same of the original plant. And this realization by construction brings to an equivalent realization of the original plant, which is equivalent to say as for all initial conditions xo, and for all u, the output of the inner-outer cascade coincides with the output of the initial system ABC. We then decide to apply this inner-outer decomposition to the stabilization of minimum phase systems and analyzing the performance losses. We start by defining a set of initial conditions which are mainly describing some forced equilibrium when u is equal to u0. We then assume to have a state feedback stabilizer for the outer dynamics, which has been parameterized by this, a value alpha O, such that the resulting outer output trajectories can be lower bounded by a certain exponential degrees. In order to construct the output dynamic feedback for the real plant, we consider an identity observer dynamics, from which we can obtain an estimation of the outer state, and we consider as the control law to be equal to the estimation of the state feedback stabilizer we assume to have for the outer system. supposing that the original system ABC is controllable and observable, and the system has no transmission zeros on imaginary axis, we can then design the controller parameters such as the saturation level and saturation level, so that for every epsilon t star strictly larger than 0, there exists a parameter alpha O star, an injection term L for the observer, such that for all alpha O lower than alpha O star, the output Y resulting from the closed loop system ABC satisfies the difference between the real plant output and the outer dynamics output, except for the equivalent static gain of the inner system, is lower than epsilon Y for all t larger than t star. And we have the stability property of the output. Here GI0 is the static gain of the inner system, and by the properties of the inner system self-adjoint being equal to the identity map, such static gain matrix is actually an orthonormal matrix. As an application to this theorem, we consider the case of an inverted pendulum on a cart whose linearized dynamics around the point P000 is presented here. And by taking into account the system data, we can solve for the algebraic Riccati equation, obtaining the stabilizing solution X, from which we obtain the inner factor in minimal realization, the outer system dynamics, and we define the stabilizer gain KO such that the closed loop outer system has the eigenvalues shown here, and we took the observer L such that the eigenvalues of the observer error are the one reported here. We can then make an output comparison between the real plant output in blue, the ideal state feedback output of the outer dynamics in red, and the resulting output of the outer system for the case of dynamic output feedback involving also the observer dynamics. And we can actually see that we are able to limit the undershoot of the output by a factor of 0.4%, to in this case to a value of 0.4% of the initial output value. And if one wants to make it even smaller, so that to reduce further the gap between the, let's say, the green and Y and blue lines, one has to reduce the convergence rate of the outer output trajectory to 0, which means that in practice we need to find another state controller's gain KO, reducing the bringing the closer loop eigenvalues closer to the imaginary axis, and the closer we are to the imaginary axis, the smaller is such a gap. Thus, to conclude, in the first part of the presentation, we just give an introduction of what is the inner outer decomposition and presented some for let's say the developed approach for strictly proper time invariant linear systems. We then show that actually these two realizations are equivalent by construction, and we can exploit such an inner outer decomposition to stabilize no minimum phase systems by using let's say a saturated output feedback controller, dynamic output feedback controller, whose design is only based on the minimum phase system good twin, the outer dynamics, and by exploiting the inner outer decomposition. As a consequence of this approach, we can analyze the undershoot performance loss of the inner outer of the original plant by obtaining an upper bound for the undershoot entity of the original system, and it's possible to reduce the undershoot of the original plant by reducing or by slowing down the closed loop outer dynamics output. Then such a stabilizing approach has been applied to the linearized version of the inverted pendulum on a cart, just to describe the effectiveness of the presented result. And thank you for your attention.